the sources of error and the ways of eliminating it or reducing it. And we have talked about the methods of reducing error. We talked about friction in the bearing, how to reduce the backlash, non-linearity, non-homogeneity in the material, all those stuff. And then temperature. Temperature is basically in certain problems you can use principle of opposite effect. Okay. Principle of opposite effect means if some positive temperature coefficient material is giving an error, you use some negative temperature coefficient material. Right? What we do? Positive temperature coefficient material gives some error, use negative temperature coefficient material. Another way of handling temperature is, especially in strain measurement, we will be studying it in detail. Use dummy gauge, or there are other two principles. Maybe in 2-3 classes we will be learning strain measurement. That time we will learn more on temperature compensation to that. Humidity we talked, especially PCBs, printed circuit boards, where humidity is absorbed by the flux in the PCBs that causes capacitance, in fact, short-circuiting and leading to problems. How to remove that? Basically, they use alcohol to remove the flux in the PCB with the help of brush, dry it, and then they use the humidity problem reduced or to the extent AC power lines. AC power lines are these kind of government power supplies that you get. Tamil Nadu Electricity Board, Kerala Electricity Board, whatever it is. And those AC lines, especially in India, it comes with 50 Hz signal and 240 volt typically for house and all. So for industry, of course, if it is high tension line, probably it will be little more. So 50 Hz is a very good news for us, because any time you make a measurement where you don't expect 50 Hz signal, in those applications you simply put a high pass filter or low pass filter. Mostly it will be low pass filter. You can use any one of the filters available and then remove the unwanted noise component from that. Okay? So any signal, for example, if I am on that particular table, I keep my thermocouple and then making some temperature measurement there. I expect a DC signal proportional to the temperature. If I see a sinusoidal kind of wave that's coming up there, popping up there, that's naturally not from the measurement. That's a noise picked up from the high power line that may be going under the wall, inside the wall. The AC lines will be going. That electromagnetic the force that is set up by the current carrying conductor is influencing our measurement. So we put this filters and then remove it. Okay. So this is the AC power. Similarly for RF interference. Today, a lot of RF signals are there, and anything that gets disturbed, you put a high frequency, low pass filter. Low pass filter will do pass all low frequencies. Any high frequency will block. High pass filter means it will pass high frequency signals. It will suppress the low frequency signals. So you use appropriate filters. This we will learn. Low pass filter, high pass filter, we will learn after CAT 1. That's a portion for CAT 1. You will understand it then if you don't know. So use appropriate. A band pass filter is basically you will have a lower cutoff frequency, higher cutoff frequency. Within that band, the signals will be allowed inside. Anything other than that will not be allowed. So the kind of frequency filters we will use, and then take appropriate signal and remove the other signals. Loading effect can be reduced or avoided using non-contacted measurement. Basically, for example, tachometer we talked about. It is not that all this is possible in all possible measurements. These are all some techniques. If possible, you can use it in your particular measurement that you are making, the instrument that you are using. Non-contacted measurement can be used for speed measurement. Earlier we talked about, you have a tachometer, you press against the rotating shaft and then measure the speed. There it is a contacted measurement. Essentially, it loads the rotating shaft and then reduces the speed. What you can do, probably you can do a non-contacted measurement, like optical tachometer. A light will be falling on the rotating shaft where there is a reflector placed, small reflector sticker kind of stuff will be placed, and according to the number of rotation, the lights will be reflected back. Counting the number of reflected rays as a pulse, you will be able to calculate the rotation of the shaft. So you basically don't touch the rotating shaft. You don't disturb. That means you don't load the system. So no loading effect will be there. So that way, non-contacted measurements you will be able to measure better. We talked about measuring temperature of substance. Of course, measuring low temperature, the non-contacted measurements are very low. It's not available very commonly. Whereas very high temperature, like temperature of molten metal and things like that, we have pyrometers where you like it will be like a camera-like instrument. You just see and then do small adjustment and match the temperature of the filament and the temperature. Okay, those stuff you don't actually touch the hot metal at all for the purpose of measurement. In a particular distance itself, you will be able to make measurement. So the temperature of the molten metal doesn't get disturbed, and there also non-contacted measurement will come in handy. Use auxiliary power source. Normally, the loading effect takes some amount of signal from the measurement because typically the voltmeter, ammeter, and all that, it takes some amount of voltage, some amount of current. That's because for its own functioning of the transducer is needed. Transducer is what? One form of signal is converted into another form of signal, isn't it? So it needs some input. Without any input, how it will convert it into output? So basically it needs some power, some signal. So that signal, if you provide all energy that is you needed for functioning, I will provide an auxiliary power source. Through auxiliary power source, I will have extra battery or whatever it is. I will supply whatever energy that you need for your functioning. Just look at that and then convert the signal. So auxiliary power source will come in handy. Instruments like voltmeter, ammeter, you will have battery. For its own functioning, you will have all battery, voltage, everything. For example, you will be giving this as a voltage in series or voltage in current in series, current in parallel, something like that. So entire loading that is needed for the operation of the multimeter will not be disturbed by the voltage source, will not be disturbed by the multimeter. But small extent, you can reduce the loading effect by using auxiliary power source. May not be, in certain cases you will be able to avoid, in multimeter you will be able to reduce. Voltmeter, ammeter, kind of stuff. Increasing the input impedance. Impedance means resistance. Impedance in general is resistance. Anything that resists, you call it as an impedance. It's a general term. Input impedance is, suppose I'm absorbing some energy. If I have a high input impedance, I will say no, I will not absorb energy. Okay, I will not absorb energy. The typical example will be glass bulb thermometer. Glass bulb thermometer, what happens? You insert the medium into the liquid. The liquid absorbs some amount of heat energy from the hot bath, thus disturbing the hot bath's actual temperature. If input impedance is high, that means the hot bulb will have less thermal conductivity. Like that. Less thermal conductivity means what? The heat will not be able to flow through easily inside. I should not say less thermal conductivity. By some means, because that would be technically wrong, by some means it should be able to try to resist the flow of heat inside the heat power, but still feel the temperature. Still feel the temperature. So you feel the temperature, but you won't simply allow all the heat to flow inside. I have a lot of resistance. Okay, so that kind of property, it won't disturb the medium to a greater extent. Increasing the input impedance will not, will actually avoid heat getting transferred to the medium, so that the disturbance will be minimal. And then still some expansion will be there, some reading will come, you will take the reading, that's okay. And mechanical example, it is very difficult to explain input impedance. Actually, in electrical circuits, electric instruments, wherever we have voltage signals, impedance means resistance. Normally the loading effect comes in electrical circuits because there will be a sensor, there will be an amplifier, there will be a filter, there will be a calibration circuit, there may be a display driver, and then display. That's how a typical electronic instrument goes. block by block. You will be able to put a square and then say this is that block, this block. You can put those circuits into those blocks. Each block gets input from the previous unit, gives the output to the next block, next block, next block. As a chain it goes. That's what is happening in most of the instruments. Any block is supposed to take input from the previous signal. If the present block is having high input impedance, it will say, I will not take much current, but I take only the information. I will not draw more current from the previous state. For example, typically an amplifier, even a filter for that matter. The amplifier will have its own power source for its own operation. So for giving the amplification, doing that operation of amplification, it doesn't draw all the current from the previous source. For example, it may be a transducer, or it may be the voltage signal that's coming from somewhere. It won't draw more current. If it draws more current, it takes more current from the sensor. The sensor value will come down. Sensor value will come down. It will die. If it is very feeble signal, it will die. If it is strong enough, the voltage will reduce. And that is what we call it as loading. Unnecessarily disturbing the parameter that we are interested in. So the amplifier will have its own power source and it will have high input impedance. So it will say, no, voltage, current don't flow, but still I will take information from voltage. Okay? So it will not draw current, but from voltage it understands what is the magnitude. Okay? So, and then it does its operation, whatever. It is amplifier or attenuator, whatever, it does the operation, gives the output and it goes. So the input impedance is something which resists the flow of energy, but still understand the information from there. Okay? So that again reduces the loading impact. And then null balance instrument, like physical balance. What you might have, a balance which normally the typical market people use for weighing brinjal and all that. Of course, today it's all electronic instruments, but at least 5 years back, you have a balance, you put weight here and commodity here and things like that. Right? Of course, if it is gold and stuff like that, commodity on the left hand side, weight on the right hand side, and then you weigh. So basically, when measurement is made, the needle will be in zero position. When measurement is made, needle will be in zero position. That kind of instruments are called null instruments, null balance instrument. So when the instrument is in zero position, it is ready for taking measurement. Deflection type measurements means like spring balance. You put the load, it comes down and shows you the reading. Proportional to the weight, it deflects and then shows you the reading. That's a deflection type instrument. This is null balance instrument. Null balance instruments, the loading effect will be nil. It will not be having any loading. Right? Fine. That's about sources of error and how to probably avoid, if possible, or reduce to the extent possible the sources of error. Okay. That's one problem. Now, any questions on that? Whatever we have discussed in the previous class and up till now. Any doubts, questions you want to ask? No, right. Early morning, we are all little inert, so it's difficult to ask questions, even if we have. Right? And questions will come provided you study regularly based on whatever the discussions are. Right. Any questions? Next couple of minutes, we'll be talking about the propagation of error, quantification and propagation. That's the two things. What is meant by propagation? If I am computing some parameter based on 2 or more measurements, then how each one of the error affect the final rating is propagation. How error propagates from one small quantity to another quantity when it is getting computed, getting a bigger quantity, a physical parameter like power, 2 by 10 by 60, n and t needs to be measured. Power has to be computed. How power uncertainty comes from what component of speed measurement error get transmitted, what component of torque error gets transmitted to the power is the subject matter for another. And then of course quantification of error. Okay. Normally when of course we had enough time earlier, for MTech students and all, only instrumentation is the subject. For you people, few instruments plus control system. Control system is actually a big topic. We will not be able to do justice in 2-3 units. Anyway, I'll try my best, but very difficult to do justice to control systems. Okay. Because of that, we don't have time. Otherwise, normally we do this exercise. We take a rod, give a micrometer or a vernier caliper, ask them to make measurements in individual students. Same shaft, same instrument, different observer or even one observer, we take 100 different measurements. We will typically get something like this. This is actually typically, I have made 100 measurement myself in the cabin. Okay. Took a rod and measured the diameters. So something like that we get. When we get the readings like this, what is meant by measurement? Measurement is the process of assigning a number to a physical parameter. A number means one number. Okay. Whereas every time I measure the diameter of the shaft, if somebody asks you what is the diameter of the shaft, let's say it is perfectly cylindrical. Cylindrical. Typically it is turned in lathe, whatever the accurate lathe that you have. The best of the lathes that you can think of. This is a turned shaft. Somebody asks what is the diameter. What is that you expect? Do you expect 50 different numbers, 100 different numbers for this? You expect only one number, isn't it? Diameter of the shaft is 50 mm, 60 mm, 20 mm, something like that. So we were trying to do something like that, but then we get so many different readings. Some of them may be same, but many of them it's all repeated. You see 50.677, 50.677. Some of them may be repeating, but then many of them are different, isn't it? So the question is how to, which number to be assigned, what number to be assigned. We put them in order. This is the actual reading in the sequence I have taken. This is after sorting it from small to big, and then we took the average or mean, arithmetic mean, and that we say that will be the diameter of the shaft. Common sense, isn't it? We have 3 readings, take the average of 3 and then take that as a diameter. That's what you do normally while taking measurement. I have slightly exaggerated and then 100 measurements and then made average out of it. But then think about it. The average may not appear in the table at all. Average is 50.651. 50.651 is there in the table or what? 50.64, 65, 651 is not there. 50.650, 50.652. In fact, 100 measurements we have made. In the 100, 50.651 is not there in the table at all. But then we assign that as a diameter for that particular shaft. You imagine our poor state. Okay. So 50.651 will be assigned as a diameter of the shaft because that is the arithmetic mean. And we also quantify when we take such large measurements the standard deviation. Standard deviation is the amount of uncertainty that is attached to that measurement. The amount of uncertainty that is attached to the measurement. So its standard deviation is 0.026 is the uncertainty in that particular measurement. To that extent, it will vary. It's a spread. The spread of the measurement is so much. So mean and spread we will say so that the measure you will have some idea. Oh, this is the diameter is on an average. This is this, and minor variation will be there. If the standard deviation is big, average is this. There is a bigger variation in the diameter. That means it is unturned shaft. For example, a raw shaft that you buy from the market probably which is not properly turned. It is only rolled or die casted. Something you take, that may be bigger variation in the diameters when you measure. So that will have more spread, more standard deviation. So this is one way by which you just say the variation in the diameters. Basically, they are all they are not error in the measurement. That's how you handle the uncertainty. Now I am not talking about error. I am talking about uncertainty. Uncertainty means what? We are expecting one thing, but then we are getting a lot of things. We are uncertain about what is to be done. Okay. Earlier we have been talking about sources of error. how to eliminate or avoid that. That topic is over, we have stopped. Or don't continue the same idea here. Okay, that's over. Now we are talking about uncertainty in the measurement and how to handle that. How to handle that. So you take the average and standard deviation express. Then next what you do is you plot a histogram. You know what is meant by histogram, right? Anybody who don't know what is meant by histogram? Raise your hands. All of you know, very good. So you have a histogram. You have bin. Normally, you divide the minimum value and maximum value that you found in the table. That entire range, you divide it into 10 bins or 15 bins or 5 bins, whatever. You divide it into bins and then count how many fall in that region. You plot it as a bar chart, it will become a histogram. Isn't it? So you have histogram. This will give you a rough idea about how the values are distributed. Where you have more values towards the middle region or in the side, the extreme region, whether you have more values popping, you get an idea. In fact, you reduce the difference between, you don't give any gap between one bar and another bar. And if the process is normally, any natural process, if you do large number of time, that will follow this so-called Gaussian distribution. That will follow the so-called Gaussian distribution. That means when you repeat this experiment large number of times, around the mean you have more number of values, and little away from mean you will have little less values, and towards extreme, either the lowermost value or the highermost value, you will have very fewer values, very little number of values on the extreme measurements. For example, if the diameter, mean of the diameter is 50.651, around 50.651 you will have more values lying, and little away from that it will be little lesser. Maybe the extreme values, either the lowermost values or highermost values, it will be less. So it will follow a Gaussian distribution, and then depending upon what type of stringent dimension accuracy your company follows, you will use 6 sigma, 3 sigma, 1 sigma, 2 sigma, all that you talk about. Sigma is the standard deviation. Mostly, if it follows Gaussian distribution, 99.7% of measurements that you have made will fall in that within that range, 3 sigma range. Okay. If you produce 100 components in 3 sigma level, 99.7% of items will fall within that. So this is normally how you quantify your errors with the help of your standard deviation, histogram, and Gaussian distribution. You generally understand. Error propagation is the last topic in that particular topic, not last topic for the day, but last topic for this. We should have completed yesterday itself. Actually, it is a spillover from yesterday's class. Sorry. Error propagation. Okay. What is meant by error propagation? I have made. We take an example and then try to work out. Let's say we have two springs. We have two springs. Spring 1 is having a stiffness of 1000 Newton per meter. Spring 2 is also having 1000 Newton per meter. But the first spring has the plus or minus 5% uncertainty attached to it. Okay? Or the error that can come is plus or minus 5%. Here the uncertainty is plus or minus 10%. Plus or minus 10% in the second spring. I used a different instrument for measuring second spring than the first one. Now the springs are connected in series. I put one spring and the back of it I put the other spring. They are in series. For some application I am using it. What will be the total stiffness? If springs are connected in series, the stiffness gets added, right, isn't it? You are aware of it? Stiffness gets added? Yes, no? No. That is when we connect it in series. In parallel. Okay. That's news for me. In series, the stiffness is added, and when it is in parallel, it is 1 by K1. Sorry. Series? Okay. In parallel, you simply add. Okay. Then you will connect it in parallel because our calculation becomes easy. Series also they can work out. So I have two springs. Anyway, the idea we want to convey is not that. So the resultant we need to compute. So you have two springs with different uncertainty. We want to know what is the total uncertainty attached to the total measure. Okay. What we need to do is first this is the stiffness 1. I mean the spring 1 items, spring 2 items. This is the nominal value or ideal value, 1000 Newton per meter, 1000 Newton per meter. The maximum error is 50 Newton per meter. Okay, 50 Newton. That's the maximum error. So the maximum value is 1050 Newton per meter. Minimum value is 9050 per meter. When we have the 5% uncertainty attached to that particular spring. And for spring 2, it is 10%, so it will be from 900 to 1100. So we have minimum value, maximum value for both the cases. So both extreme values we compute. What we wanted to do is the parameters are getting added, K1 plus K2. The stiffness, when the combined stiffness is K1 plus K2. This K1 I measured with 5% uncertainty. This K2 I have measured with 10% uncertainty. I would like to know what percentage of uncertainty will be there in the effective total stiffness. That is what I am interested in. So I am trying to compute 950, 1050, 900 and 1100, which are minimum and maximum values. And then find what is the worst case or formula is not okay. So I'm finding what is the worst case error. So on lower side, both lower side and higher side, it happens to be same. It need not be same always. An instrument may have uncertainty of plus 50 minus 100 or minus 100 plus 50. It can have error in any way, but then here it happens to be same. That simplifies our problem. So the minimum value of stiffness in K here will be minimum of this value and minimum of this value. That will be the total minimum for the effective stiffness. Okay, that happens to be 950 plus 900. It is 1850. On the higher side, it is 2150. You are able to follow me? Okay, I am finding out what is the minimum value of this effective K, or what do you call it? The effective K. K1 plus K2, and that is the worst case on the minimum side. On the best case, on the higher side, that is also the extreme case. Other extreme case is the maximum value. Maximum of this plus maximum of this. That will be the maximum value this effectively can have. So I am finding the minimum effective, maximum effective, that happens to be 1850 or 2150. The difference is 150. Okay, the error is 150. Okay, so now the percentage of error we take. The nominal value is 2000 Newton per meter. The error is 150. So find out the percentage of error. That happens to be 150 divided by 2000 into 100, 7.5%. Okay. So this is 5%. This is 10%. This is 7.5%. Up to this is clear, right? So when we have 5 and 10%, here it will have 7.5%. What can you say about how do you relate this 7.5 to 5% and 10%?
Average.
That's an average. So whenever you can, whenever you are free, you can take some more examples and work out. Whenever the parameters gets added or subtracted, the uncertainty attached to them are averaged. The uncertainty attached to them are averaged. So even you can take another formula where there is some parameter minus some parameter, and still you can work out the final value will be average one. Okay, so it's only average for addition and subtraction. So averaging is done in uncertainty when you have plus operation and minus operation, adding and subtracting. Okay, so that's one point that we want to stress. Another one, you take a power calculation with the speed of 500 rpm and torque of 200 Newton meter. Okay, and both parameters are 3%, and the uncertainty attached is 3%, 3%. That means this is also with 3% uncertainty I am making measurement. This is also with 3% uncertainty I am making measurement. If that's the case, what will be the uncertainty that is attached to the power? So power P is 2 pi n t by 60. This is with 3%. This is with 3%. What percentage individually? Of course, these are all constants. There is no uncertainty attached to it. They are constants. What percentage of uncertainty will be attached to the power is the question that we have here. Follow the same procedure. I have just copied the snapshot from my book, so it looks smaller. I don't know whether you will be able to see. 3% of 500 rpm is 15 rpm, and so 15 rpm with you find out the nominal speed. Nominal speed, how you 2 pi. What is rpm? 500 into 200 divided by 60. This will be the nominal rpm. Okay, normal value or nominal value. And with the 3%, 15 rpm less. Which is rpm here? This is rpm. The lowermost value will be 485, and lowermost this 3% of 200 is 6 Newton meter. So if 6 goes means 194 divided by 6. In these places, if you use this, that will be the lowermost power that is possible. Okay. So if you compute nominal power, it happens to be indicated power, nominal power, whatever it is, 10,466 is the nominal power. Okay. If you use minimum values or maximum value, both are same, because it's plus or minus 3. Whether you add 15 and then compute the percentage of error will be same. So on the best case, they found out speed plus error, that means here 15 you add, this will be 2 pi 515 into 206 divided by 60. This is the on the higher side, this is on the lower side. Anything you can do. Find out this power, the difference between this will be the error in power, isn't it? This is the power, nominal power that we expect, ideally, if there is no uncertainty attached to both speed and torque. There are 3% uncertainty. So I am finding what is the, if my, what is mean by the error? Instead of 500, my instrument may show 485. Okay, actual value will be 500. My instrument will show 485. Instead of 200 Newton meter, my instrument may show 194 on the lowest side. It can go up to 515 and 206 on the other side for each parameter. Any reading between 485 and 515 I can get for RPM. Any reading between 194 and 206 I can get for torque measurement. I am finding only the extreme values because extreme only it is important for me. That's a limiting value. Okay. So I am taking the best values and then find what's the highest value my instrument can produce while This is the actual value. What is the false reading? But the error, what is the maximum error my instrument can produce? That if I simulate, that will be 2 pi 250 into 260 that happens to be 11,104.08 back. So the difference between that is 637. Nominal power I have calculated already into 100 I get 6% as the error percentage on the positive side. If you take the lower value, again it will become 6%, but that will be on the negative side. So if this is plus or minus 3%, this is plus or minus 3%, here I get plus or minus 6%. Here I get plus or minus 6%. You are able to understand whatever is taught? Okay. Right. Now, what is the lesson that we take from this? That's an illustration. The rule that we learn from this is when the parameters get multiplied or divided, one divided by the other parameter, both in multiplication and division, the parameters get the uncertainty get added, not parameter. The uncertainty gets added. So here the uncertainty is 3%, 3%. It may be 3%, 4%. It need not be same. I just took, if it is 3% and 4%, what will be the uncertainty here? It will be 7%. So don't relate that 3%, 3% will be equal in multiplication, things like that. No confusion on that. It can be any percentage. Randomly I took, and it happens to be the same value. Okay. So in multiplication and division, the rule is the uncertainty should get added. Addition and subtraction, the uncertainty gets added. That's all for error, sources of error, and the error propagation and management. Any questions on that?
Division also we add the errors. Should we subtract?
Yeah, you take it as an exercise. You work out and see that you will be surprised to see the percentage gets because actually here also you might ask the same question. So while plus also it's getting average, minus also it's getting average. You didn't ask the same thinking should have come there. That's because it's plus or minus, and we only work on extreme values. You will see that even with some parameter divided by some parameter, you can find out minimum, extreme minimum value, extreme maximum value, nominal value. Nominal minus any one of these extreme values will give you the error. The error divided by nominal value into 100 will give you percentage of error on the final parameter. You will see that take it as a tutorial for take home work and try it out. If it is not moving, come back. We will sit and sort of. Okay. Just stop the video once.